So, hello. First of all, I just wanted to say a huge thank you. And I want to say thank you to all of the amazing speakers that we've seen over the last 2 days. Really exemplary talks, as good as any talks or better than the many conferences that I've visited. So it's truly incredible. So thank you, everyone. Can I just get a huge round of applause for all those people? And I want to thank Rob Pike for passing me on my phone interview when I joined Google, and also him and the rest of the team who graciously and generously accepted me into the Go team, and also trusted me to represent the incredible work that they do. It was truly a privilege for me to be a part of that, and I think it's become a huge part of my life, and I feel like I'm better for it. And I want to thank the community. So, over the last few years, I've been told incalculable times that I'm an idiot and that I don't know what I'm doing, and that Go is going to fail. And I think everyone in this room and all of the people in the greater Go community are proof that they're wrong. So thank you to all of you. So in this talk, well, you can applaud yourselves if you like, and you should. Thank you. So I joined Google and Go simultaneously a bit over 4 years ago in February 2010. And at that time, not many people knew much about Go. It had only been in public for about 3 months. And, for a lot of people, it was pretty weird. For me in particular, I came from a dynamic language background. I'd spent the last 10 years writing web apps in a variety of languages. And to me, Go seemed like there was some stuff that was missing, and it really, or different, or just weird for no reason. And so I wasn't even sure that I was going to like it in the first place. So taking the job was really daunting for me. But in the intervening time, I decided to embrace the language full on. And I just want to share with you, what I've learned since I started learning Go 4.5 years ago. And so the best place to start, I guess, is with interfaces. So when I first approached Go, I was accustomed to thinking a lot about types, and particularly about classes. I've been working in Python and PHP and JavaScript. And so the lack of inheritance and subtype polymorphism and parametric polymorphism left me hanging a little bit. Instead, the language emphasized interfaces. And for me, previously, I'd never really given a lot of stock to interface. It was just that annoying thing that I had to type implements foo all the time. But so the Go approach, as I guess we all know after the last couple of days, is to keep interfaces small. A stringer can pretty print itself, and anything that implements string is a stringer. That is the definition of Go interfaces. A common example of an interface is the I/O reader. It's basically a Unix pipe, or the read end of a Unix pipe. It emits a stream of binary data. This is an implementation of reader. It's actually one that Brad described in our panel discussion. It's a byte reader. It just is a byte that implements reader. And calls to read will just fill the buffer with that byte. It's kind of cute. And one thing that we do with interfaces is we wrap them. And here's an implementation of a reader wrapper. It's called log reader. And it just embeds a reader, and any calls to its read method are delegated to the embedded reader, and then it logs the number of bytes read and an error output, and then just returns the values from the original reader. This is really useful in debugging. And so by wrapping the byte reader with a log reader and then just calling read, we can see that it works. We see the log message and then see that the buffer was filled with A's. And what we're seeing here is the composition of interface values. We have a byte reader value. We wrap it with a log reader, and it gives us something else, the composition of two things. And then we can continue to wrap these wrappers to build chains. Here we have a byte reader that's wrapped with a limit reader to make it end of file after a meg has been read from it, and a log reader wrapping that. We pass that into IO copy, which is writing to another interface implementation, discard, which will throw the data away. So when we run this, we see a bunch of log messages showing that copy is using an 8K buffer, and that on the last read, it reads 0 bytes and returns end of file. And this is an example of just using the composition of interfaces to compose small pieces to implement complex behavior. Furthermore, it's a demonstration of programming with interfaces and how interfaces separate data from behavior. So copy is a function that operates on two interfaces. It takes a writer and a reader. But it can't know. It's not just that it doesn't want to know, it cannot know about the underlying data structures, and it doesn't care. It just takes the reader and writer and does its thing. And so in this sense, we can program with behavior, and that's a really powerful concept. Looking at another interface, the sort interface, which we've already discussed this week, it just describes the operations that you need to sort a collection, any collection. It provides a length, less to compare two elements, and swap to mutate the collection and swap two elements. And so from the sort package, we have this int_slice type. It implements those three methods for a slice of ints. It's provided there as a convenience because it's common to want to sort a slice of ints. And then we can pass that int_slice into the sort function to sort, say, this list of primes. It's also worth noting that there is sort.ints, and you can sort the ints with a function alone if you want. But now looking at a sort example, I'm going to go with this thing which is an example in the standard library, and that's sorting bodily organs. We have this organ type, which describes an organ in its name and its weight, and it also pretty prints itself. It's a stringer. And also note that the weight field is in grams, and it also pretty prints itself by appending a G. So if we print the weights of the brain, heart, liver, pancreas, and spleen, we can see them nicely displayed. But when I'm working with organs, I like to have them in order. It's important. And so to sort a list of organs, we're going to introduce this organs type. And so type organs is a slice of pointers to organ. And it knows how to give the length of its slice and also to swap elements in the slice, but that's it. To get sort interface from this, we embed the organs type in these by name and by weight types. And these two types implement less methods to compare either the names or the weights, respectively. And by embedding the organs type in each of these structs with less methods, we compose types to create sort interface values, or sort interface types, effectively. And so to sort a slice of organs, you wrap it with one of these types and pass it to sort.sort. And so we can see that of these organs, the pancreas is the lightest, and the brain starts with B, but I guess you already knew that. Another interesting wrapper that you can use here is reverse. So reverse is a function that operates on a sort interface, and it returns another sort interface. And all reverse does is delegate to the original less method, but swaps the order of arguments, so it provides the reverse sorting order. Interesting to note that sort.interface's other methods, len and swap, are unchanged. Reverse still provides those. But so when we sort these, we see that the liver is the heaviest of those elements, the massiest. But you've probably seen a lot of this before. But it's important to note that these aren't just like cute tricks. It's actually how we structure programs in Go. So for example, earlier this year I started working on a modular audio synthesizer in Go. And the way it works is you have various processors that you connect with links. They have outputs that go into the inputs. But the way the audio is actually computed is you call the engine's process method, passing it a buffer. It calls its parent processor's process method, passing it that same buffer, and so on. So this is effectively the same as IO reader, except we don't need the error semantics. And the buffer must always be filled, so we don't have the number of bytes read either. But this is an example of a real program whose fundamental piece is a chain of readers, or a chain of processors, rather. Another example of these composed interfaces is Roshi, which is by Peter Borgon. Where are you, Peter? He spoke earlier, that superb talk about using Go in production. Roshi is a time series event store developed at SoundCloud. It exports a public API via HTTP, I believe, of insert, delete, and select for these types. But that same API is actually implemented at different levels throughout the system. So the server type, which is the HTTP server, it talks to a farm via this same interface, and the farm talks to each of these clusters using the same interface. And I think this is a really elegant design that exhibits this property of composing interfaces. It doesn't matter that part of it isn't actually a Go interface. The important property is that it's this sort of comprehensible, layered approach. So, why does this work? It's because interfaces are the generic programming mechanism in Go. So we don't have, classes or inheritance. We don't have a lot of other features for structuring code in Go and providing the dynamism that we need to write code conveniently. Instead, we must turn to interfaces. And this makes the sort interface more cumbersome than just writing a less method. And I know Brad has been hacking away on writing a less method-based sort using reflect and all sorts of crazy hacks. But the important point is that sort is slightly more verbose, but it means that the rest of the system is a lot simpler. And I think, and as I'll continue to discuss, less is more. Interfaces by design force us to think about composition, and then as a result, to write composable code. Even if you look at embedding, which is the closest thing that we have to classical inheritance in OO, although it's fundamentally different, even embedding is principally about composition, and this says something. Interfaces are also just types, and interface values are just values. You pass them around, you can put them in structs, you can pass them in channels, and that makes them orthogonal to the rest of the language. And so that makes them work really well in the context of the language and increases their power. And finally, interfaces separate data from behavior. If you think about a class bundles data with the functionality, and it's kind of inextricably linked. Whereas Go has types, and types can have methods, but an interface is something ethereal in a sense. So a great example of this that has already been discussed is the handler func type, which implements the serve HTTP function, which means that it implements the HTTP handler interface. But its underlying data is a function. And so for me, that really clearly illustrates how, it's not a class implementing a method, it's a function implementing a method. So what I learned from working with Go interfaces is to think about composition. It's better to have many small, simple things than one big complex thing. And also, I realized that what I'd previously thought of as a small thing was actually pretty big. Go interfaces are typically one method. I don't think I'd ever really encountered interfaces in the past that had one method. But yet, this is kind of like the fundamental part of the entire philosophy of Go interfaces. And finally, I learned that some repetition in the small, as is the case with sort, is fine. It's okay to copy the odd piece of code when it has benefits that knock on in the large and make things simpler overall. So let's talk about concurrency. My first exposure to concurrency was in the traditional realm of C, and then later Java and Python. And that was just the traditional threading model using locks to share memory and so on. Then later, I started using event-driven models like Twisted Python and JavaScript in the browser, as well as Node.js, and I thought this was great. I saw the event-driven model as a way of writing code safely that was high performance and could serve many clients concurrently. And so when I saw Go, I thought, wow, this is an easier way to do this same thing. I can write high-performance code that serves a lot of people, a lot of clients simultaneously without having to split my code up into callbacks. This is a win. And it is. But that's not all. And I had questions. Why can't I get a Go routine ID and wait on a Go routine and kill it? That would be convenient, right? Well, the Go way is a bit different. So as we know, Go routines provide concurrent execution. Channels give us a convenient way to express communication and synchronization between those Go routines. And select enables us to compute on channel operations. It's very powerful. Let's look at a quick concurrency example. Who here's done the Go tour? Hey. This example from the Go tour, which was authored by Russ, it has you implement a function same that compares to binary trees. So the trees are, have the same contents here, but they're differently balanced. So you need to iterate over them in order to compare them simultaneously. So to walk a tree, it's really simple. This is a tree node with left and right nodes. You have a walk function, which is recursive. It will walk the left hand of the tree if it's non-nil, print the value, walk the right hand of the tree if it's non-nil, and continue in that fashion. And if I run this on this generated tree, we see 1 through 10. Pretty simple. But to compare trees, we want to do them simultaneously because the trees could be of arbitrary size. We don't necessarily want to just flatten the trees into slices and compare the slices, because that's kind of cheating. But to do it concurrently, and I think a lot of you have probably already done this, we turn our walk function into a function that's called from a Go routine. And it takes a channel. Instead of printing the value, you send the value to the channel. In the Go routine, you call walk and then close the channel once the traversal is completed. So this walk function here takes the root of a tree and returns a channel of integers on which the elements of the tree will be sent, and then the channel is closed. So to use this relatively simple walking function is really easy. This same function takes 2 trees. We create walkers for each of them, W1 and W2. And then we do 2 receives from each in this for loop and compare the values to see if the values have diverged, in which case we return false. Or if one of them is closed before the other, we return false. But otherwise, we only return true if we've finished walking at least one of the trees. And so if I run this with 2 different trees, we should see true and false, which is good. But what if we wanted to do this, so who here actually completed this in the tour? So fewer people. Okay, so we need to work on the sticking power of the tour, I guess. But what if we wanted to do this without channels, without Go routines? I think here's an example that does that. I've changed the signature of walk to return this walker value. And the walker value implements a next method, and the next method has similar semantics to the channel receive. It returns a value from the tree and a Boolean to indicate whether the walking is finished or not. And so the structure of same looks pretty much identical, but the implementation of the walker is not pretty. We have to maintain our own stack, and in each frame of the stack, we have the current node in the tree that we're traversing, and I've called it PC because it's basically a program counter. But as you can see inside next, we have like 3 different states. We're either traversing the left-hand side of the tree, or we're emitting the value, or we're going down the right-hand side of the tree, or we're going back up the tree. And writing this code it took me like 10 minutes, and it was wrong the first time I ran it. Whereas when I wrote this code, it was right the first time. Well, not the first time, but I was learning Go at the same time. But now that when I write it, knowing Go, it was easy. But there is a problem with this. If an inequality is found in it, then a Go routine might be left blocked, sending here. So we need some way to clean up, and that's where select comes in. So if we add a quit channel to the walker here, pass it into our recursive walk function, and it passes it to its own calls to the recursive walk function, we can select on either sending the value to the channel or selecting from the quit channel. If the quit channel emits a value, we want to return and just shut that walker down. And then in the same function, we just add a couple of lines. We create a quit channel at the top, and then we defer the closure of that channel so that when this function exits, any of the walkers, which I've also given the quit channel, are shut down. So why can't I just kill those Go routines? Why can't my walk function here just give me the Go routine IDs, and then I say defer, kill Go routine 1, kill Go routine 2? And why did I have to just build that myself? Well, there is a reason. And the reason is kind of subtle, and it comes down to thread locality. As soon as Go code is able to understand the Go routine in which it lives, programmers will start to rely on that. People will use thread local data storage, and then that means that any code that is called from code that cares about that also needs to care about that. And that means that it will defeat the concurrency model entirely, because I can't run code in a Go routine if I know that some code that I'm going to call depends on me being in this Go routine. And so this is an example of something which I'll describe. Sorry. So why does this work? Why does this model work? The reason why is because it makes concurrent code easy to read and write. But the important thing is that it makes concurrency accessible. And it encourages you to decompose independent computations. So these two walking of different sides of the different trees are totally independent computations. They don't need to be linked. And so they encourage us to decompose them, and the decomposition happens naturally. And so it's the simplicity of the model that makes it flexible and useful. Channels are just values, just like interfaces are just values. You can put a channel in a function argument. You can have functions that operate on channels just in the same way you have functions that operate on interfaces. You can put channels in structs, and so on. You can even have types that channel types that implement interfaces. I've actually seen that happen before. And because Go routines are invisible to Go code, it means that you can actually use concurrency anywhere that you need it. So it's always there. And that's an example of less being more. If there was more to a Go routine, if Go routines were visible to Go code, you wouldn't have this power. So what I learned from Go's concurrency model is that it's not just for doing things faster. It's actually for writing better code. Okay, syntax. This is fun. So who here was kind of struck by Go's syntax when you first started? Did anyone have a problem with it? You can admit it. Yeah, tabs. So I did as well. I was used to some of the conveniences from other languages. I also came from Python. I didn't mind the braces. I don't really care about that. But it was mainly what was missing that bothered me. We had no getters and setters on fields, no map, filter, reduce, zip, no optional arguments. Some of these things are not strictly syntax, but I bucketed them this way anyway. But the Go way is to favor readability, and that's not something I'd really thought about deeply before. It offers you enough sugar to be productive, but not too much. So if you think about getters and setters or properties where you can make a assignment or a read from a field into a function call, that means that something that looks like a read or something that looks like an assignment can be anything. And that's a real that leads to control flow that is hidden from you, and you need to follow any assignment just in case it happens to be a property assignment. Whereas in Go, you just have to write methods and have the client of your code call those methods. And so the control flow cannot be obscured at all. The sort of functional primitives for manipulating lists were really useful to me in Python. So for instance, if I wanted to map a slice of ints and add 1 to each of them and get a new list, I would write that. And it's really succinct. It's nice and cute. But in Go, you have to write a loop. And at first I was like, oh man, that's boring. So I have to make the slice, iterate over A, assign into the slice. And it's a bit more verbose, but it makes the performance characteristics of what's happening really obvious. And I learned that this is actually really important. You see the allocation here, and you also get more control. If you wanted to mutate the list in place, instead, you would just write A there and get rid of the allocation. And this code's easy to write, so it doesn't really matter in the long term. Another big thing, probably one of the biggest things I missed, was optional arguments, which I was very used to in Python. Anyone miss optional arguments? You shouldn't, but I'll explain why. Instead, the Go approach is to use variations of functions in your type. So you have, this is from gzip, you have new writer and then new writer level if you want to specify a non-standard compression level. Or you can use an option struct, Or, Rob made a great blog post on using variadic lists of functions, and there are other approaches. But the important thing is that in each of these approaches, we're not adding to something, except a package, but we're not adding to the function. We're not making the function more complex. We're adding another small, simple thing, right? Not making something more complex. So why does this approach work? Well, it's because the language resists convoluted code. You know you're doing something wrong because the language is making it hard for you. And when the control flow is really obvious, it makes it really easy to read other people's code and navigate in that code. It makes it easy to read your own code. Instead of making things bigger and more complex, we keep them small and add more smaller things. Each of those small things easy to understand in itself and easy to document. And so this makes Go code easy to read. And with GoFunt, it's easy to write that readable code. So what I learned from Go's syntax and these minor features is that I was often a bit too clever. I remember feeling like an absolute hero writing really fiendishly clever JavaScript code. I actually met some of my ex-colleagues for whom I was doing that, and yeah, they weren't really that happy about it a couple of years down the track. I'm sure all of us have been in that situation at some time. So I really appreciate Go kind of preventing me from doing this. I also appreciate the consistency, clarity, and most importantly, transparency of Go code, being able to see what the code is actually doing. We saw the allocation when I was mapping effectively over that list before. And I sometimes miss some of these conveniences when they would have fit really well, but it rarely happens. Not a big deal. So let's talk about error handling. People love talking about error handling. I came from environments that almost exclusively used exceptions to handle errors. And so in Go, I was immediately struck by if not equal nil, return and I felt like I was doing that all the time. I felt like it. I wasn't necessarily, but I felt weighed down by this. And so the way Go handles errors, as a quick summary, is that it codifies them with this error interface. So anything that has an error method that prints the error as a string or formats the error as a string is an error. And then an error value is just a value, like any other value in the system. You program with it. And so error handling code is just code. And it's interesting to note that the error interface actually started as os.error. And for Go 1, we made it built in. And so this approach leads to seemingly more verbose code, but actually I've found in practice, if you compare comparable code with exceptions, it's about the same if the exceptions are well handled. So why this works is because error handling is important. Does anyone disagree with that statement? All right, I didn't think so. So Go makes error handling as important as any of your other code. It's not something else. Errors are just values, and they fit into the rest of the language. You can have channels of errors. You can have, errors are interfaces, but they can be in functions and so on. And so as a result, you think about your error handling code the same way you think about the rest of your Go code. You try to write it correctly, and you try to write it elegantly. You structure your code such that you don't have to mundanely handle errors, just as you write code that doesn't mundanely do other things. You strive to write clear and correct code. And so because we use the same language for errors as we do for everything else, there's none of this hidden control flow that you get with an exception model. So that immediately improves readability. You don't have to look at any function call site and think, is this going to throw an exception? Brad was telling me that apparently in Java, sleep can throw an exception. And so to sleep, it's 5 lines. You have to wrap it with a try and catch in case the sleep was interrupted, which is, it's crazy to me. And so I think that error handling is just another value. That errors are just another value is an example of less being more. We get a lot more power and clarity, or clarity in general, by not having extra mechanisms surrounding errors. And so what I learned from this is it actually made me realize that you have to think about errors all the time to write good code. Exceptions had made it really easy for me to not think about errors. It was always an afterthought. Well, not always, but often, my Python code would explode with a runtime error, and then I would go and find where that happened and think, oh yeah, okay, that map access could throw a key not found error. That's bad, so I'll make sure I handle that in the future. I'll make sure I remember that. Whereas Go, instead, anytime you do anything like this that might return an error, you have the error return value is there. You have to think about it. And so as a result, my Go programs are way more robust than any of the programs I wrote in other languages, and that's true. And it's one of the reasons I started, instead of writing bash scripts, just writing Go programs instead. They were a bit longer, but at least I knew they weren't just going to crap out. And so I don't miss exceptions at all. Packages. So when I first came to packages, I thought, cool, it's namespaces. It's kind of like Python, kind of like Pascal from back in the day. But I found that capital letter visibility rule weird. Did anybody find that weird? Anyone go, that's not my style. I don't do that. Beginning with a capital? What is this, English? Ugh. I didn't like a package per directory. I didn't like this prescribed directory structure. Oh, I have to keep it all like this. I have to put it where? No, I won't do that. I was also disappointed by the kind of rigidity of the package interface, that I couldn't reach in and annotate types with additional methods or override methods, the way I'd kind of become accustomed to doing in Python. And I'm sure there are Ruby users here who do stuff like this all the time, even adding to the built-in types. And so this kind of disappointed me. So the Go way with packages is they just provide a namespace for exporting types, functions, variables, and constants. Visibility is at the package level, which Rob highlighted in his keynote. And names are exported when they begin with a capital letter. And this gives us this beautiful orthogonal concept because it applies to all of those top-level declarations, as well as functions in method signatures in interfaces, and also fields in structs. And so the huge benefit of this is that it's great for readability. You can look at any name in a package, in the source code, and see whether it's part of the exported interface or not. And it's also great for design because it couples your naming decisions with interface decisions. So, naming is really important. And when you're typing the name, you think about whether it's a public name. You're going to think about what the user is going to do. And often, when you're designing interfaces, you want to give the name something that makes sense to the user, not something that makes sense to you necessarily as the programmer here in this package. It's important for them out there. And that person out there could be you, right? The package structure. Packages can be spread across multiple files, and they permit you to share private implementation with this kind of informal code organization. If you look at the HTTP package, it's one package with a number of exporter identifiers, and it's like 30 files? I don't know. It's a large number of files, and you wouldn't want that to be in one package, and Go doesn't force that. And that's why they must live in a directory, because the path to that directory determines the import path of that package. And this has a huge effect, as we've seen, as users of the Go tool, of users of go.org, and so on. The build system can locate dependencies from that source code alone. Finally, Go forbids modifying package declarations from outside the package. But that's okay, because we can get similar behavior using things like global variables. Like in the flag package, we have this usage variable that lets us override the usage message when people submit bad flags. Or registration functions like HTTP handle, which actually mutates a shared map of HTTP handlers. And there are other techniques as well. But all of these techniques, they give the flexibility of this monkey patching approach, maybe not quite the same flexibility, but they're on the package author's terms. The author of the package has given you blessed ways to mess with the package, and that's nice. And it's worth noting as a subnote that all of this depends on Go's initialization semantics, which Rob discussed. And those semantics are so clearly, nicely defined that we don't even notice how integral they are to the kind of code that we write every day. So why does this work? Well, the loose organization of packages lets me just start writing code. I don't have to think about the name of the file that I'm writing. If I'm writing a command, I just go edit main. If I'm writing a package, I'll often just edit whatever the name of the package is, .go. And then I can move things around between files as things grow and change without changing any of the public interface. But the way names work actually encourages us to consider the public interface a lot. And this leads to good naming in general and simpler interfaces because we're thinking about them. And with source code as a single source of truth containing all of the information required to build Go programs, it means that we don't have any other metadata files that can get out of sync. And it enables incredible tools like godoc.org and Brad's Go imports tool. And finally, the predictable semantics of packages just make it really easy to read other people's code and understand how other people's packages will work in interaction with yours. So what I learned from working with packages is that I should prioritize the consumer of my code, even if that consumer is me somewhere else. And it taught me to always be thinking about that hypothetical person who's going to be using the API that I'm building. It also stopped me from doing gross stuff, like reaching in and overriding methods from other things, and so the behavior of a package would change based on whether I'd imported some other package or not. Which, I didn't think they were gross at the time, but now I find them revolting. And packages are rigid, so basically packages are rigid where it matters, and they're kind of loose where it doesn't. So you can kind of just work away, and I don't feel restricted by it. And that's why I think the package design is actually my favorite part of the Go language. And finally, I'd like to talk about documentation. So first of all, I thought docs were pretty boring, and I never wanted to write them. Does anybody else share this opinion? Seriously. In other teams that I work with, nobody ever documented their code at all, in 90% of the cases. Horrifies me now, but it's true. But GoDoc reads docs from Go source code, and at first it seemed to me just like PyDoc or JavaDoc or something like that. But unlike those two, it doesn't support any kind of complex formatting inside or any other metadata. And why is this? Well, GoDoc just reads regular comments that precede the exported identifiers, and then it presents them in various contexts, like the HTML that we're all familiar with on the command line. And I believe Russ even wrote a template that emitted trof, and when we did Go 1, he produced a Go book that had a PDF of the entire Go standard library, which he read from start to finish. So that's kind of cool. We also have example functions, which are kind of cute. But so the presentation is nice. We get all of this with just that bit of code. And the reason why this works is because GoDoc wants you to write comments that are good comments. It doesn't want you to write comments that will turn into pretty HTML. It wants you to write comments that look good in the source code. Whereas JavaDoc, this is actually a stripped down version of the example from Wikipedia of JavaDoc. So the original was much more hellish than this. But they have this, it's ASCII art, it's, all these this little sub-language they've invented, which is really useful, right? Because when you hover over in your IDE, you'll see that string and all those things. But as a programmer, as a reader, this function is probably a line long, yet why should it be preceded by a 6-line comment? And so another little side benefit is because all GoDoc comments, by convention, begin with the name of the identifier they describe, if I grep for valid move, I will find this line in my output. And what could be more helpful than that? So what I learned from working with GoDoc, and I guess also working with the Go team, is to write documentation as I code. I sure as hell wasn't committing anything to the Go core that wasn't documented. And I found that writing this documentation really improved the code that I was writing. Because as I was writing it, I had to think about how to explain it. And as anybody who's taught anyone anything will tell you, the best way to understand something is to try and explain it to someone. But there are many more examples that I could give of ways in which Go has challenged my preconceptions and that I've learned from using it. The overriding theme is that at first, something seemed wrong. Something didn't mesh with how I thought things should work. Then after a while, I realized that it was on purpose. It was a design decision. And that those decisions are in the name of making the language and, as a result, Go code itself better. And I think, sometimes you just have to live with the language a while and, be programming with an open mind to see that. So what are the lessons that I learned from writing Go for the last 4 years? First of all, code is communication. I think working on such a large open source project, that has come home to me more than anything. And when you're communicating with people, you need to be articulate. You need to choose good names. You need to give them names that mean something to people and that are not too long, that are easy to remember, and that signify something real. You need to design simple interfaces so that people can understand how to use your code. You need to write precise documentation. So there's a difference between precise documentation and what a lot of people think of as good documentation. You should try to say only exactly what needs to be said and nothing more, and certainly nothing less. And finally, don't be too clever. I think everyone in this room has been burned by a programmer who's considered themselves very clever by what they were doing. And the same is true in a conversation. If someone is being a real smartass, you don't want to talk to them. So don't be that person. I also learned that less is exponentially more, and I'll give credit to Rob for the phrase. He wrote a great blog post by the same name, and if you haven't read it, you should read it. But less is more is something that you hear a lot, but in this case it applies particularly aptly, because any new feature that you can propose, and I should mention that features, by definition, are useful. I often have these conversations where people are saying, oh, you should add this to Go, it's really useful. That's the base criteria for even opening your mouth to discuss something. You're not going to say, oh, I got this idea for a feature, it's kind of dumb. But any new feature can weaken the existing features that exist. If you add a feature, it multiplies the complexity of the system that you're in. When you're writing the code, when you're reading the code, you have to think about interactions with other features. And so that complexity, it defeats orthogonality. And orthogonality is vital because it enables composition. And composition is key. It's key to writing good software. I learned that you shouldn't try to solve problems by building a thing. You shouldn't think, what's the thing that's going to do all this for me? Instead, you should find simple tools that you can compose together to solve the bigger problem in total. You should design good interfaces, and that's a pretty, vague statement, right? What does it mean, a good interface? It means that you shouldn't over-specify. If you give a Gopher too many restrictions, he ends up like the one on the left there, unable to think for himself, just a cog in a machine. If you under-specify, you end up with the guy on the right, who's up in the hills somewhere, stoned out of his mind, not cooperating with anyone. Whereas in the middle, if you find the sweet spot, you get a happy, helpful little guy who'll jump in and surprise you with his ingenuity and flexibility. And so when you design interfaces, you should think about this. You want something that is well-defined enough to be useful and predictable, but not so specific that it can't be used in a variety of contexts. And so I think Go itself, if you think about Go as a user interface, has hit this sweet spot in terms of good interface design. Finally, simplicity is really hard. I've lost count of the number of conversations that I've had with people in the community and people on the Go team about how to make something simpler. And there was always a solution that we could have taken that would have solved the problem. But we had to actually spend a lot more time to find the simple solution. And sometimes that means spending more time to revisit things that already work. When we did Go 1, we revisited almost everything that we'd ever done with a critical eye to how it could be made simpler. What could we take away? What can we do without? So invest that time. And so all of these things that I learned, I already knew them intellectually. Like everything that I've just said in these last few slides were all things that I could have told you, yeah, of course that's a good idea. What do you mean? Yeah, simplicity, everything should be simple, of course. But it was using Go and working with people like you that taught me to internalize those lessons. And now I think about them not just when I'm programming, but also in a variety of other contexts. So Go made me a better programmer, and I, with mild hyperbole, say I think it also made me a better person. That was the gopher sound, you got it right. So I have a message for all of you and all of the gophers around the world. Let's build small, simple, and beautiful things together. Thank you.